where do you want to start with this? Do you want to introduce the project you're working on, or start from like the very ground there? Feel free to go which direction you want to.
I think a good start would be kind of like the background and like what made me make an FPGA, because no one just like decides I'm gonna build an FPGA. It's not like a thing you just build in your backyard, because you're effectively designing silicon that's reprogrammable.
Mhm.
And so I've had FPGAs for a while. They're really cool. One of the things you can do with them is basically just design any sort of reprogrammable circuit onto it, or you can design things like CPUs, you can design graphics chips, you can do signal processing stuff. Effectively, an FPGA has a few thousand to possibly tens of thousands of logic cells that represent basic binary operations, and or XOR. Sometimes you have MUX configuration stuff. They have a little bit of some fancier things like SERDES, which are called serializer deserializers, we shorten it to SERDES because that's faster to just say.
Mhm.
You also have DSPs, which are signal processors. You also have like BRAM, which is block RAM. Typically, you have like things like DDR, which is in everyone's computers nowadays.
Mhm.
You
Mhm.
have SRAM, which is a little bit less common, but still is used today. But BRAM's kind of it is just a slab of memory on some tile of the chip, and it's there. It's
Okay.
very simple.
Mhm. Mhm.
Uh, the problem I was running into was every FPGA is proprietary, meaning the entire silicon's proprietary, the tools around is proprietary. Thankfully, over the past however long, uh, people have created open source toolchains like
Mhm.
Yosis and NextPNR. Uh,
So
they've
those
done
were what again? Let me.
Yosis,
Yosis.
YOSYS,
No.
and NextPNR.
Okay. And next PNR. Okay. Cool.
And basically, because of all these proprietariness, you need to buy the license, you need to have very specific environments, like you can't be using this on like Arch Linux without going through great lengths of patching the software to get it to work correctly, kind of like
Mhm.
what we had to do on NixOS. Um, so people have created Yosis and XPNR, which are just gone through a lot of reverse engineering to figure out what is this actually doing
Mhm.
and how we can do this without the proprietariness. The kind of problem that I ran into with this is because you're still relying on the proprietariness of hardware, some of these reverse engineering efforts haven't gone to great enough lengths to create a suitable replacement that that is better or comparable to the existing toolchains that are proprietary.
Mhm.
So sometimes you might run into little issues like on Lattice ECP5, like the JTAG, which is just this little five pin serial connection. There's an IEEE standard. Basically, just think of just like trying to do GDB, but it's for hardware. You
Mhm.
can hook
Okay.
it up
Okay.
to a CPU and be like, I want to see what's going on the CPU. And on Lattice is, for whatever reason, is not deterministic. If you try using it, uh, because routing is not deterministic, because it is constraint solving very NP hard problems, you don't always get the same routing every single time.
Mhm.
That routing change can change the timing to the JTAG,
Mhm.
meaning you cannot predict what the JTAG signaling is going to be, and so then you always get garbage.
Mhm.
The weird thing is, this is not a problem on the proprietary EDA, which seems weird why the open source tools have this problem and not the proprietary one. They
Would
must
that
be doing some
just be a
magic.
reverse engineering issue where they don't know exactly? Again, I'm any comment I make here is going to be from a position of I don't know much about hardware. I would assume because they have to reverse engineer it, whatever they're doing with the proprietary version is not entirely clear. So the result you have with the open source implementation does not align with that. Maybe I'm off base here.
Yeah, I'm not really clear on the exact like behavior of the
Hmm.
problem because it's still very weird, but it's been documented online of like ECP5's JTAG of being just not that well to work with.
Mm-hmm.
And so I was like, well, I'm having all these problems with the open source stuff. Um, so I'm going to create an open source FPGA. And I basically had a very simple idea to get started, which was just to design a LUT. And a LUT is a lookup table,
Mm-hmm.
which is the actual logic cell of an FPGA. Which, if you look at how it works, it's just think of a truth table that you can reprogram. So you have a few inputs, you have a few outputs, and then there's just a bunch of muxes that control when certain values are, or when the LUT is configured in a way, it can then do and or XOR stuff like that. And then from there I started scaling up, and then I added things like CLB, which is a configurational logic block, which has LUTs inside of it. Added things like mux trees, which then allow you to kind of carry signals around a little bit more in complex ways. And it started building into an actual FPGA. And when I looked at it, I was like, oh, this is actually like starting to become usable. Still no hardware yet, but at least I was able to get a simulator inside of Rust and run effectively a Blinky, which is like the hardware version of a Hello World. It's basically just light goes on, light goes off. Just that just repeats on until there's no electricity. Which,
Mm-hmm.
yeah. And then I was like, well, this is pretty cool that I have now an FPGA that I have designed, and it's designed in a way of being called parameterized, meaning a lot of hardware is very specifically designed. So you write all of your Verilog, which Verilog is the language of hardware. Basically, it is a representation of wires and stuff. It's
Mm-hmm.
kind of a functional programming kind of way of doing it. That's kind of the way to represent hardware. And what I was using was something called ROHD, ROHD,
Mm-hmm.
Rapid Open Hardware Development. It is a Dart framework. It's Dart like what Flutter uses and what Google's been using for a few things.
Okay.
And yeah, so this is a thing Intel made. They've been working on it for like 5 years now. And so I basically have a way of being able to expand my FPGA by just changing a number.
Mm-hmm.
Because FPGAs are and silicon tradition or usually are grid laid out. So you have a grid. So like on a CPU, your grid would contain all of your cores of your actual CPU. On an FPGA, your unit of compute is the logic cells. So I was
Mm-hmm.
laying down all the logic cells in a grid, and then if I want more, I just say the grid is now this much bigger or this
Mm-hmm.
much smaller, which is very declarative.
So at this stage, everything was being done in a simulator.
Yes,
Yes. Okay.
so I was able to simulate, well, yes and no.
Mm-hmm.
So I had a Rust simulator that would take the description, would effectively a descriptor file that I had emitted out during the generation time of the Verilog and stuff like that, because there's a Dart program that I wrote that just is what you use to generate all the files for actually getting the silicon manufactured, describes every minute detail for simulation and for actually like, you know, creating a program that you would load onto the FPGA.
Mhm.
And so I at least got enough for able to do a Blinky, and I was able to start to do Nix builds of just building and getting a GDS file, which GDS files basically is kind of like the G code, which is like the 3D printer format.
Mhm.
But think
Mhm.
of that, but for silicon. So it describes this is exactly like what to put on every single layer of the silicon
Mhm.
and how to like manage the substrate and all that. It's very complicated format. It takes literally an entire day for my desktop to process all the routing, every test, every check to make sure this thing will not explode or fail to manufacture.
Mhm.